Nie, włączyć, ale przestawić. No. No, bo oni to włączyli. Dlatego
Weź to mówić głośno.
Dobra, jest ok.
Razer.
Spróbuj bez tego.
Jest Razer.
Włączony. Dobra, poczekajcie, teraz jeszcze mamy. Ale co mam teraz wyłączyć? No.
Mam Razera.
A nie, jest okej.
Mam wyłączyć tą kamerę?
Jest okej.
Jest okej.
Jest
Tutaj,
okej.
tak? Teraz mam.
Albo desktop, jakby.
Aha, tak, mam.
Chyba nie widzę teraz. Ja tego jeszcze nie, bo nie widzę tego. Wait, muszę ustalić kompletnie to systemem. Nie, poczekaj, mam parę screenów i po prostu ona była tutaj przed chwilą. Tak, do tego jest po prostu czas. I teraz gdzie mam? O, tutaj. Teraz mogę. Dopiero wtedy powiększam to, tak? Czy najpierw wyświetlić? Czy najpierw zrobić? Nie, jak zrobię to na całość, to nie będę mogła do tego wejść. Muszę wejść teraz, gdzie to jest.
Nie ma.
Nie, było tylko, że...
Nie masz na screena.
Nie, gdzie ja jestem.
Tutaj.
Poczekaj, nie wiem, gdzie ja jestem.
Nie, no tu.
Powiększ to.
Tak,
Tutaj to. Teraz.
Gdzie jest to moja rozdzielczość? To jest to. Dobra.
Piszę. Pierwszy slajd. I w początku wyświetlę.
I teraz...
Slajd.
Czekaj, bo to się robi. Tak. A dlaczego jest coś źle? Jak jest jakaś krew? Czyli
Nie widać tego w internecie.
ale taka krew powinna być? Czy to jest dziwne? No,
Start. So welcome everyone.
jak powinno było?
Bez fokus.
Może powinnam tutaj wyłączyć. No to nie, to powinnam była wyłączyć ten dźwięk.
Let's try it. Okay, now it's good. It's good. So welcome everyone at this new academic year Tuesday seminars. It's our pleasure to welcome our guest today, Professor Dorota Rosińska, who's going to tell us about 10 years of gravitational wave astronomy. But before we start the lecture, I have some information for those who are attending the seminars as students, so especially PhD students and master's students. So just the general rules of passing the subject is that you are allowed to be twice absent, and you can also connect via Zoom. The Zoom link is provided every week, but it's the same. So that's also the justification if you attend by Zoom, but you have to somehow prove your presence. So the best is screenshot. So that's from the general point of view of organization, and let's have some adventure with gravitational waves. Given by Dorota Rosińska and Dorota.
Before that, we promised that we will introduce our
I thought it's after, but it's fake.
You prefer at the end? Well, okay.
We can do it before, as you wish.
I think that, maybe some people would like to escape, before the end. So we wanted to just to introduce two new PhD students, three new PhD students. So if you can come here and just say a few words about you. So Michał, yes,
Actually, I draw.
So maybe we'll start with Joy.
Okay. So I am Joy Shankar Majumdar, and you can call me Joy. So I am from India. I have done my master's from Banaras Hindu University, and there I have worked on high energy astrophysics, more or less on the blazars, like multi-wavelength analysis of blazars. And here I have joined Vukash and Marius, and I'm going to work on multi-wavelength transients. Okay, that's it.
So hello everyone, I'm Sakshi Maurya and I'm also from India, and I have done my master's from Banaras Hindu University, and here I joined the Professor Rosińska. So I'll be working on the numerical simulation of gravitational wave sources, particularly in neutron stars. And in my previous work, I was working in high energy astrophysics, particularly in AGNs. Thank you.
Thank you.
So hello everyone. Some of you probably know me. I'm Michał Małkowski. I'm from Gniezno. I've done my master's degree in this observatory, and currently I'm doing my PhD degree on binary lens microlensing with Professor Radosław Poleski.
Thank you. Super nice that you are with us. So have fun with your PhD. And now, well-known Professor Dorota Rosińska, an expert in neutron stars and also gravitational wave astronomy. I think Dorota doesn't need a big introduction because everyone knows her or heard about her. That's a great example of a fantastic career in astrophysics.
Oh my
Dorota
God.
spent years in France and Spain, and she joined the observatory in 2018, and we are very happy to have you here and that you start the seminars this semester.
Yes. Thank you very much for the introduction. I'm a little bit surprised with such kind of highlights concerning my life. Let's concentrate on our topic. So today, this is not so easy because today I would like to give some summary of 10 years of gravitational wave astronomy, which was born with the first detection of gravitational waves, which were just 14th of September 2015. Here you have the birthday cake. We celebrate this birthday of the first detection all together with Polgraph team. A team of Polish scientists which were involved in the first detection, but we started our journey with LIGO-Virgo-Kagra observatories in 2008. So we waited a little bit to have the first detection. So they were observations, but we haven't seen anything for many, many years. So the first detection, oh my God, it is not working. Sorry. I'm afraid that I cannot use it because I don't have any possibility to do this. There's not sufficient amount of USB, so I will use my fingers simply. So, okay, the first detection, probably some of you know, but maybe I will remind you that we are using such kind of signature for saying what kind of detection we are just talking about. So the first one, GW, it means gravitational waves, and then you have the date of the detection, so 14th of September 2015. the first detection of gravitational waves, and it was from very interesting source, I mean from the binary black hole. So I think that most of people know this, but to remind how it was looking like. Then when we detect this, we keep silent because it was necessary to perform data analysis to be sure if there is really a real signal or not just some artifact or just some noise coming from some cars or maybe even from our collaboration, because from time to time we used to inject, just make some hardware injections or blind injections, I mean, shaking our detectors and just looking if we are able to find signal in our data. So we needed time for that. And then finally, at 11th of February, simultaneously in all institutes which were involved in the first detection, we announced that we have detected gravitational waves. Here you have a spokesman of LIGO detectors, David Wright, who just said this famous sentence, we have detected gravitational waves. We did it. So it was really very fantastic beginning. So two detectors, LIGO, which are located at Hanford and Livingston, 3,000 kilometers from each other. They just detected the signal. I have the signal here on this T-shirt. Yes, I was in, by the way, I was a student of Rayton high school. So I'm just doing something like that. Yes, that the first detection of gravitational waves is here. And it turned out that, both detectors just have signal which was consistent with each other in Hanford and Livingston. And for this effort, three our friends who are in LIGO-Virgo collaboration, Ray Weiss, Barry Barish, and Kip Thorne, received the Nobel Prize. It was not only for the very first detection, but also for decisive contribution to the LIGO detector, because for many years, I mean 100 years since Einstein predicted that it was the consequence of general relativity that gravitational waves could appear. There were many efforts to try to catch gravitational waves, and 4 generations of scientists and engineers tried to do this. And finally, after 100 years, we did it. So Ray Weiss unfortunately passed away several weeks ago, but he was very active in science until the end of his life. And also the other two, Kip Thorne and Barry Barish, are involved in science concerning gravitational waves. So there is just a very short summary of that, what was detected. I mean, there were 2 black holes with masses 20, without around 29, around 30 solar masses and 36 solar masses. They just spiral each other, just 8 circles, only 8 circles. Then we had the merger of 2 black holes, and finally we observed one rotating black hole with 62 solar masses. So if you are doing very simple math, 36 to 29, you see that it's 62, am I right? Everybody agree with that? Not everybody. So this is 65, but 3 solar masses were emitted in gravitational waves. So this is what we have seen. Yes? That's here in Hanford. Here you see the signal in Hanford and Livingston, which agree with each other. And then what you see, you see that there is very characteristic signal for compact binary coalescence, because you see that frequency and amplitude is increasing in time. When they are closer and closer to each other, the frequency is higher and the amplitude is higher. The frequency in gravitational waves, it is just twice the orbital frequency. So if they are closer to each other, you have higher frequency. It was really something very, very amazing, because for the first time ever, we see that we have opportunity to test general relativity in strong gravitational field. And you have seen plenty of relativistic phenomena. For example, before the merger, the velocity was 60% of velocity of light. This is characteristic signal, which is called chirp signal, that the frequency and amplitude is growing in time. And here you have the most important parameter, which we are measuring, thanks to that we have compact binary coalescence. There's this chirp mass, which is that function of masses of compact objects before the merger. So this is the most accurate parameter which we are measuring. And this chirp mass we are getting directly from in spiral phase. So it depends on the frequency and the derivative of the frequency. So we are measuring from spiral phase the chirp mass, as well using post-Newtonian calculation. We can also determine the spin of two black holes, and also spin of black holes or just compact objects, as well as the mass ratio. So if you have the mass ratio, which is not very accurate one, we can extract information about solar masses. So this is a short summary how many important information we got thanks to the first detection. For the first time ever, we detected gravitational waves. So it was really something great that after 100 years, we've had so precise instruments to be able to measure very tiny effect like amplitude of gravitational waves coming from astrophysical sources. The second thing is that the signal was coming from two black holes. Nobody before observed two black holes. And it was predicted that by our team, Tomek, Chris Belczyński, and students involved in that the first detection it should be two black holes, but majority of people at this time thought that it would be two neutron stars, because we knew that neutron stars exist, binary neutron stars exist, but nobody observed before two black holes or one black hole, yes, that they were just candidates for a single black hole. So we have detected binary black holes, and something was also very interesting, that situation that the masses of these black holes were quite huge, comparing to candidates for black holes from low mass X-ray binaries, for example, that the masses were 30 solar masses and even 60 solar masses. And it was a proof that during the Hubble time, mergers are appearing in the universe. Mergers of two black holes are appearing in the universe. And it was such kind of high masses could indicate that maybe they were formed in dynamical scenario, or maybe coming from low metallicity environment, because these masses were higher than we thought before. And the luminosity, the energy emitted during this short time, I mean shorter than 100 milliseconds, all the process lasted just milliseconds. So the process when you have two black holes, when they are dancing around each other, 8 orbits, then merger, and then the ring down, it was less than 100 milliseconds. And if you take into account electromagnetic energy emitted by the universe, all stars and all galaxies, the energy emitted in electromagnetic wavelengths is 100 times lower than the energy we detect in gravitational waves, 10 to the power 56 erg per second. For the sun, you have 10 to 33 erg per second. So this is really huge energy emitted in gravitational waves. So this I think that most of you know, because it is 10 years. So finally, after many, many years, we are trying to fulfill this last image, how looks universe in gravitational waves. So some basic things: gravitational waves are consequence of GR, and they were predicted by Einstein in 1916. They carry energy, and it was just giving us hope to detect gravitational waves, thanks to the results of Trautmann and Robinson, that gravitational waves are real, that we in future we would have be able to detect such kind of oscillation of the space-time. What is very important that gravitational waves are different than electromagnetic waves. Electromagnetic waves are propagating in the space-time, but gravitational waves are oscillations of the space-time itself. And they're very weakly interacting with the matter. So thanks to that, we can see the signal as it is emitted by the source. They are not absorbed, they are just really carrying this information from the source, almost not changed. So they are propagating with the velocity of light. There was assumption, but thanks to our studies, data analysis, and observation, we proved that this assumption was true, that gravitational waves are propagating with the speed of light. And it was just assumption, and we proved that it is possible thanks to that we had observation in both in electromagnetic wavelengths and in gravitational oscillation detected by us. So some basic things concerning how gravitational waves are interacting with matter. So gravitational waves have two polarization, and this is not 90 degree like in case of electromagnetic radiation, but this is 45 degree. And what we measure, their amplitude, which is called H plus and Hx. And this is what you see. This is the effect of gravitational wave propagating perpendicular to this billboard, yes, showing what gravitational waves is doing with matter. So if you have a circle and gravitational waves is propagating to this direction, you see that you have stretch and squeeze in perpendicular direction. Then the circle is coming to the shape as before, and then we have opposite situation. And what we are measuring the changes of the length of the detector. So our detectors, they are gravitational wave interferometer detectors, which are like that you have two arms. In the case of our detector Virgo, European one, there are 3 kilometers arm. In the case of LIGO, there are 4 kilometers arm. And having even so long arms, it turns out that the effect of gravitational waves is very, very small. I mean, in the case of 4 kilometers, the changes are 10 to minus 18 meters. So this is really very small difference, what we are able to measure. Our detectors are the most precise instruments which we ever construct on the Earth. So this is really amazing that such kind of tiny changes we are able to measure with the length of the arm of our detectors. So currently we have two LIGO detectors in Hartford and Livingston. I don't know, I'm afraid the battery is gone. So I cannot show it. It's on. It's on.
You can use the manual.
Okay, so maybe I can jump. So okay, so you see that currently there are two LIGO detectors working, operational one. We have also Virgo detector, which is located in Pisa, close to Pisa in Italy. And we have Kagra detector, Japanese one. and we are doing so-called O4 scientific run, and it will last until 18th of November. So we are observing universe. You have also GEO 600, the first generation detector, but with very low sensitivity. So it is dedicated to some particular objects which are looking for example, rotating neutron stars in low mass X-ray binaries, but not contributing to main observation concerning coalescing black holes. So there are our detectors, two LIGO detectors, our Virgo detector, and Kagra underground, for the time being with low frequency. So the main goals of gravitational wave astronomy is just very important contribution to fundamental physics, astrophysics, and cosmology. And there are only a few questions, but there are plenty of questions which we hope to answer, thanks to that for the first time ever, we have completely different way of discovering universe. I mean, for the time being, we observe, using our eyes or just hearing universe. Concerning gravitational waves, I can say that we can feel universe, how universe is just shaking, our detectors and also making influence on us. So first of all, this is something like that we observe hidden universe, mainly black holes. Merging black holes are the most important source of gravitational waves. They are the strongest sources for us, just merging black holes. So thanks to that, we have very great laboratory for testing general relativity, and just we hope to be able to answer if Einstein's theory is the correct theory of gravity. We are taking into account also different kind of modified gravity theory to see which theory is really valid, taking into account black holes, coalescing black holes. What is the nature of black holes? How is mass black hole and massive black hole? Thank you so much. And massive black hole can form. We also hope to try to solve the problem. What is the basic state of matter in dense environment like a neutron star, when we have extreme, very high density? What is the origin of gamma ray bursts, and also contribute to cosmology? What kind of model is the best one for that? So there are many questions we hope to answer. And now I'm coming to, I just would like to put control on that. What time is it? Okay. Where I am, fine. So concerning astrophysical sources of gravitational waves, this is very important that they should be compact, relativistic, and highly asymmetric. And what is interesting, that each of source has very characteristic signal. So using Einstein's theory, we can tell what kind of object is emitting gravitational waves. Here you have an example of burst signal. Here you have this signal, what is called chirp signal from coalescing compact binaries. And we are just focusing not only on known sources of gravitational waves, but also we are open for unknown one. So let's see what would be the next signal. Maybe we can vote. What do you think? If there would be a supernovae, asymmetric supernovae, yes?
So may I ask you what relativistic means?
Relativistic, I mean in the sense that accelerated with high frequencies objects, compact objects. So there are many information just included in this highly in the relativistic. So compact objects and spinning with high frequencies. So there are just we are working in 4 groups in LIGO-Virgo-Kagra collaboration, and we are focusing on periodic sources, on coalescing compact binaries, on burst signal, different one, on stochastic background, and of course on unexpected sources. So for the time being, we have observed only merging compact binaries. So binary black holes, there are majority of our sources, binary neutron stars, merger. Unfortunately, for the time being, we have only 2 of them, and neutron star black hole binaries. So this is how we are, this is our history, how we are working. We have from 2002 to 2011, we had only the first generation detectors, and here you see the horizon to which we are able to detect binary neutron stars. So the first generation detector, and then our aim is just to have 10 times more sensitive detector. So it means that if you are measuring amplitude, amplitude is inverse to the distance to the source. It seems that if we are 10 times more sensitive, we will have 1,000 more objects in this volume. So we are doing this step by step. So we are making improvement of our detector, and then we are having some scientific run, which are called O1, then O2, O3. Now we are doing O3, O3C, and each time we are starting with better sensitivity. If there is better sensitivity, we have the higher volume from which we can see the object. And for after 3 compounds, observational compounds, we have 90 mergers. But then now we have lots more because we just published the catalog 4, at which we include also the first run of O4A. So mainly we are observing gravitational waves from black holes. This is very famous event, GW17017. I think that each of you know this very good and also observe this from electromagnetic wavelength. But you know, it would be not fair if I will not mention this, because for us, it is really something very important, because having detection of gravitational waves, let's see, from this O1, they were just only binary black hole. And then in O2, when Virgo joined at the end of this O2 combine, so thanks to that, we had much better localization than when we have only 2 LIGO detectors. We have detected gravitational waves from binary neutron stars, and at the same time, 70 electromagnetic observatories were looking to this direction. So this is the history, how it was looking like, that we had a merger, then 2 seconds after the merger in gamma ray, it was the observation of short gamma ray burst, and then around 11 hours after that, we had that it was detected and it was visible that we have kilonova explosion. What is interesting that I think that I should mention here that Bogdan Paczyński predicted this, that gamma ray burst can be produced by a merger of 2 neutron star or a neutron star with a black hole. So for the first time ever, we prove it, because we have observed the merger, and then 2 seconds after, it was short gamma ray burst observed. And also about 20 years later, Bogdan Paczyński predicted that if we have such kind of merger, we should observe kilonova explosion, and we observed this. So here you see this characteristic chip signal, GW017, then gamma reverse 2 seconds after, and then you see that the objects appear in the galaxy as which we had the merger. So it was kilonova. So it was really very big success of both of multi-messenger astronomy. We can say that there was the first detection of multi-messenger astronomy in which you had gravitational waves with the very broad ranges of electromagnetic frequency observations. And from that, it is really very big shortcut because I think that I don't have time to talk about it, just only to remind you that thanks to that we have this gamma ray burst and we had the gravitational wave observation, we measure the velocity of gravitational waves, and we obtained that this result, that this is the speed of light with such kind of accuracy. So it's really amazing. We tried to repeat this analysis in the case of the second binary neutron stars, which we detected, but unfortunately it was 5 times more far away than that one, which was only 40 kiloparsec from us. So there was not electromagnetic signal coming from us, no gamma ray burst, no visible in the other in the electromagnetic wavelengths. So this is one thing which is very important. We also contribute to measurement of the Hubble constant, but it was not very accurate. But we have done such kind of estimates. We also show, thanks to this observation, that heavy elements, a lot of heavy elements are produced during this merger. So let's say 50% of Mendeleev table, it is produced in such kind of mergers of 2 neutron stars. The gold, platinum, uranium, etc. are produced during such kind of merger. So where we are now. So here you see we are measuring our sensitivity by looking at average distance to optimally oriented to neutron stars binaries. So for the first observing run, only LIGO was working, and the distance was 80 megaparsec for 2 merging neutron stars. Then it was a little bit better for OAUW and Virgo join, and then we had this first detection of binary neutron stars. Then OAUW a little bit better, and now we are using OAUW, the first OAUW scientific run. So for LIGO, you have such kind of distance. For Virgo, it's around 50-55 megaparsec, and Kagra is not so much sensitive. And this is our future. We hope that OAUW will happen, but it depends also of funds for LIGO, because you know that there is Trump decision, 40% cutting budget for science, and we'll see how situation will look like with LIGO. So when we have better and better sensitivity, we're detecting more and more events. So now we have more than 300 strong events from universe, but we publish only information concerning confirmed gravitational wave signal, including O4A. So now I focus on this. What are the most important things? So at the end of August, our catalog paper was published, so you can have a look what kind of sources we have there. There are basic information concerning masses, what kind of object they are, spins, distances, etc. So this is in Gravitational Open Science Center, so you can have a look at this. And the multiple publications are supposed, with results, are supposed to appear within just 1 month. So for the time being, we have one paper, very important, concerning confirmation of Hawking theorem, concerning the surface of black holes. But the next papers will be focused on different things like cosmology and fundamental physics. And I would like to just come to that thanks to that we have much better, this is not so much visible this is the first detection, and this is not visible how noisy it was. But here you have very similar signal to the first one. The distance is very similar and masses are also similar. We have GW 25014, so it was 14th January this year. And we confirm Hawking theorem saying that if you take into account the surface of a black hole before the merger, so if you have two black holes and you add the surface of two black holes, it turns out that the final surface of the final black hole is higher than the surface of these two black holes before. And Hawking wants to know, just when he got information for the first detection of gravitational waves in 2015, he died in 2018. He asked us if we can prove it that his theorem is right using GW 150914. But at this time, the sensitivity was not sufficient to prove it. And now you see that having the radiance of the black hole before the merger and after the merger, we are able to extract this information and prove it that he was right. So this is the summary, what kind of objects we are observing. And blue circles correspond to black holes. So you see that we are dominated by black holes, and orange ones are corresponding to neutron stars. Here you have the masses. And this is comparison what we have it from electromagnetic observations. So there are candidates for black holes here and here. So for many years, we have only these candidates for black holes. And you see that during very short time, 10 years, we have more than 200 binary black holes coalescences. And we are able to measure the masses of two components and the final masses. And what you see here, that we are able to detect really very massive black holes, in the sense that for the first time ever, we detected intermediate mass black holes. That you have, if we define that intermediate mass black holes are those with masses higher than 100. So here you'll see that we have plenty of these black holes with masses above 100 solar masses. Here you see that we have only two coalescences of two neutron stars, and among them this one famous one. And we have some candidates for a black hole with neutron stars. So we hope that thanks to this detection, we would be able to extract information what is the maximum mass of neutron stars. So this is the first intermediate mass black hole, when we had 66 and 85 solar mass black holes, and the final one was above 100. So this is this famous GW 190521. And since these black holes are having quite huge masses, they are just in such kind of gap at which we think that we should not have stellar black holes, because we have so-called per-instability phenomena. So it seems that probably we should have a gap. It depends on the paper you consider, but something between 50 solar masses to 120 solar masses, where suppose that we should not have black holes in this per-instability gap. So this is idea that maybe the origin of these two black holes is just coming from that it was in a dense environment, and they are the effect of the merger of lower mass black holes. But this is just question mark if it's true or not. But what we observed is the first intermediate mass black hole. So we are starting to fulfill the gap concerning neutron stars. This is one of the famous sources, GW 231123. There is the most massive system we have ever observed. You have two black holes, both of masses above 100 solar masses, and the final black hole is about 200 solar masses. So when you look at this view graph, I don't know if it's really visible. Here you have, if you take into account all black holes, distribution of black holes observed till now by LIGO-Virgo-Kagra, you see that there is such kind of distribution, and you see that there are two gaps there around 10 and 30 solar masses. But this object is really very, very massive. You are just going, to very high masses. So this is exceptional source. Also concerning spins, there are quite huge spins. So one of the guess is that maybe they are coming also from dynamical interaction. It was detected quite recently, I mean, in 2023, by two LIGO detectors, because at that time Virgo and Kagra was not observing the universe. We have also a black hole with a neutron star. That's the first such kind of detection. And we hope that we could say something about the interior of neutron star, because we thought that maybe there, thanks to tidal forces, this black hole could be disrupted. But it turned out that the mass ratio was very small, so it seems that a black hole just eaten this neutron star by once. So unfortunately, we haven't seen any effect of tidal disruption in this case. So, there are just some highlights, because it is not possible during this short time to say everything about that, what we observe. So just some examples. So as you have seen, there are two mass gaps, and we are starting to fulfill this mass gap, the lower mass gap, because we are looking what could be the maximum mass of neutron star. So in some cases, we have question marks. We don't know if there is very massive neutron star, let's say with 2.6 solar masses, or very light black hole, for example, in this case, GW9300814. Here you have the other object. We think that there is a black hole above 3 solar masses, but anyway, you see that we are starting to fulfill this gap, just trying to find the solution if there is a neutron star, very heavy neutron star, or very light black holes. So this is the example of one very interesting object, which was the first result published in 2004. And this is very busy slide, just again showing the distribution of masses of black holes and the rate which we obtain for binary neutron star, binary black holes, and neutron star black holes. So we think that concerning two black holes, they are merging every 5 minutes in the universe, and for two neutron stars, every 1 minute in the universe. So very amazing, but our horizon is not so, we don't have sufficient sensitivity really to observe all of these mergers. So now I'm jumping, so this is some highlights from this 4 observing runs, and we are going to better sensitivity and to future detectors. So in Europe, Poland, University of Warsaw is a representative of Poland in Einstein Telescope preparatory phase. So we are actively working on that to have funds and to prepare everything to build future detector, Einstein Telescope, which would be 10 times more sensitive than LIGO. So thanks to that, we would be able to observe more than 1,000 events more than in the case of LIGO. So we will have plenty of sources. I will show you what kind of thing we could observe. This is not decided yet at which place it would be located. We have 3 candidates for localization of Einstein Telescope. It would be underground detector to eliminate noises, and it would be sensitive starting from 1/3. It is very important because thanks to that, we could be able to observe much more massive black holes than we are observing now. And also to see the spiral phase in more details. And Cosmic Explorer is planned also at United States, but it depends on the funds. So better sensitivity from lower frequency. And here you see the difference in the sensitivity. For LIGO, you have this blue line. And for Einstein telescope, this is one of the solutions, this is green one, and Cosmic Explorer, this violet one. So you see that we will be able even to go above redshift 10, even 100 for intermediate mass black holes. So we could see all mergers of black holes at our universe. Here is the beginning of the universe. We are here. This is the design sensitivity for LIGO, how much you can see of the universe with the current detectors. Here you have the first intermediate mass black hole system, GW 190521. So this is how far away we can go. And with Einstein telescope, you can observe really all the universe, all mergers at the universe which are appearing. I like very much this picture. This is one of the last pictures I would like to show you, because the first thing, we are in the center, yes, so at the center of the universe. And you can see how far we can explore, what is the horizon to which we can see something with the current detectors and future detectors. So the blue one is what we can see now. And let's concentrate first on binary black holes. You see that we see at least 50% of merging black holes. Yes, this one. But with Einstein telescope and Cosmic Explorer, we will see all mergers of black holes at the universe. If you have a look at neutron stars and black holes, you can see that it is predicted that with the current detectors, we can see only a few of them, so we are consistent with that. But with Einstein telescope, we can see again all of them. Concerning neutron star binaries, only we can see few of them, and this is consistent with the situation right now. Many people are asking, have you detected again 2 neutron stars? Why haven't we seen anything electromagnetic wavelengths and so on? We don't have hope to see many of them because of our sensitivity. But with the Einstein telescope, you see that majority of neutron stars would be able to see. So we could, explore this topic, and I'm pretty sure that it would be very important for our knowledge of neutron stars. So this is our future. I hope that it will happen. And this is a summary of that thanks to gravitational wave astronomy, we have a new way of exploring the universe. This is complementary to electromagnetic observations. And there are here some examples of our the first detection of 2 black holes, the first detection of 2 neutron stars, the first detection of the intermediate mass black hole. For the time being, we have confirmed more than 200 mergers, but you can have a look at GraceDB. This is open for everybody, so you can see what is there. All alerts, all information, all detection are in GraceDB, so you can have a look at that. And then we have also, you know, we are waiting with the release of the data of O4. It would be just at the beginning of 2026. And please be patient, because I hope that before the talk today, it would be more paper available on AstroPH, but not yet, because we promised that for 10 years of gravitational wave astronomy, 10 papers on different topics, important one, at which we are including results of O4A, would be published, but they are not available yet. Just this paper of this event, the loudest event at which, thanks to which we could confirm the Hawking theorem about the surface of a black hole. What have we learned from this gravitational wave window? Plenty of things are here written, this is just only part of gravitational wave astronomy, because using our detectors, we can only explore high frequency range of gravitational waves, starting from 10 Hertz to 10 kilohertz. So this is here, but we are here. But there are also very important observation and events. I think that Gosia gave a talk here at the observatory. Yes, she gave a talk here at this PTA pulsar timing and the results from that. So it was quite interesting result. I have no time to discuss about this. We hope also to have LISA, so we could observe not only mergers of white dwarfs, mergers of some galaxies, and high mass black holes and disruption of black holes, but also we could see the same system which we are observing at LIGO-Virgo, but at the stage when they are in bigger separation. So this is quite important. Lisa can tell us, for example, in 5 years, 3 hours and 2 seconds, you will observe a merger of 2 neutron stars or 2 black holes. So this is really very interesting. And at the end, I would like to go to the slide, which I like very much, because we, with Tomek organized and Polgraf's team, we organized LIGO-Virgo-Kagra conference in 2019 in Warsaw. And there were more than 300 people from LDK taking part in that, 500, I think, remotely. And for the first time ever, it was possible for our collaboration to invite Andrzej Trautman, and he gave a talk. Thank you very much, Marek, because Marek really made a big effort to convince, how to say, maybe not to make pressure, but you were very pedagogical with that, to ask Trautman to come to our collaboration, because first he confirmed and then he was afraid that maybe it would be too difficult for him to give a talk, but finally I got permission from our spokesman to invite somebody like Trautman to give a talk. So it was really great that professor who just gave us hope that we could see gravitational waves thanks to his papers and studies that gravitational waves carry energy. He met finally people who confirmed this by observation. So it was really very big success. If you are interested, there is an interview with Andrzej Trautman and also Barry Baruch on the Astronarium number 84. So thank you so much.
Thank you, Dorota, for a great overview. Do we have any questions or comments? Dorota?
So I have a question about the binary constant measure that you showed on your final slides. And the answer time was pretty large, so I think it was between 10 and 700. Yeah,
So you think that it should be lower?
I don't know. Well, my question is why the answer time, why is pretty so large? 10 and 700.
No, because this is why it's such kind of big error bars, yes, concerning this. No, I think that it's in fact, I don't know exactly why it's so huge, because we have
if you estimate a wave based on 2 events,
2 events, yes.
then the error is huge. And essentially, we estimated mostly on 1 event, so the closest one.
Yeah.
Because the contribution of the other event is much smaller. So essentially, this is the statistics of 1 plus event.
Okay.
So did I understand well that the next phase, till the next phase to the O5, there's going to be a break, right? In the
Yes, it would be a break because we have to do, you know,
The
modernization, the upgrade of our detectors. But what is good, I just thought, okay, this is O5, and we have to wait for Einstein telescope and Cosmic Explorer. The first prediction was 2035 for Einstein telescope, but we don't believe with Tomek that it could be possible to have this Einstein telescope, you know, at this, I think 40, 45, something like that. So what to do with that? And people, if we have funds, we will try to monitor universe beyond O5.
Okay, and the time when O5 will be on track, which is 28, right? Or something like this.
Yes.
So they're going to be more than 2 years of break. And this is all detectors that's going to be upgraded, right?
Yes,
So,
because we would like to do at the same time, because
okay.
very important, at least very important is just to have good localization. If you have just one
You need-
detector, you don't have localization. If you have two, we are using triangulation method. So in this way, this is really something like 2000 square degree. It's really terrible. So we would like to observe universe, all detectors at the same time. And we'll see, you know, it really, for LIGO, it depends a lot on funds, because maybe now it was something what was considered that if the budget is cut so much, 40%, there was a suggestion that maybe instead of making upgrades, just being at 04 and making this longer, yes, for a longer time. But finally, the decision is that we are finishing at 18th of November and we are preparing, because this is new technology, we really need time to be prepared for 05.
Thank you. Any more questions, comments, nothing on Zoom? See? If not, let's thank Dorota. Thank you very much. And it's a notebook somewhere, so if you are master students of each student, please put your name there. And the next week we meet at the same time.